Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to actually go through a very important equivalence theorem, basically, that has to do with orthogonal matrices. But just to get started, I want to just kind of show one of these computation problems with a very important result from the last video. So at the very end of the last video, I talked about how if you have a square matrix that's orthogonal, which really means orthonormal, right? You have one of those, I should say, if and only if the inverse of that matrix is the transpose of it, okay? So an easy way to show that something's orthogonal is to just take the transpose. So here, UT would just be 0, 0, 1, 1, 0, 0, and then 0, 1, 0. I think I did all that correct, yes. And then if you just do literally UT, also UTU, right? If you just compute those out, you will just see that, let's just do the first kind of row here. So let's do this, right? We get, 0 plus 1 plus 0. So we're getting 1 right there. And then, actually, let's just do one more because the next one's kind of different. So then if we do this and this, right, we get 0, 0, 0 again, and 0. And so we get a 0. And you just keep going through that. You really would get the identity matrix, the 3x3 identity. So this just proves that this thing is orthogonal based on this very important if and only if theorem. So this is the equivalence theorem that I was talking about that I want to just kind of go through in this video. So what it basically does is really what I have up here. It tells us sort of what orthogonal matrix kind of gives us. And so it's worded as, so Q is an n by n, right? And all of these are equivalent. And I will actually prove in this video this equivalence. But first I want to kind of just talk about what these things are saying, I guess. So I look at it as like Q being orthogonal, which is like this kind of thing, right? Means that this will happen, it's equivalent to this statement, and it's equivalent to this statement. And these two statements are also equivalent, okay? But a lot of times I just look at it as Q orthogonal if and only if this, Q orthogonal if and only if this. These are kind of like important properties, basically, of orthogonal matrices. So what Q basically is something in math we call an isometry, which is really a length-preserving transformation. That's basically what this word means. And these show up like all over the place. There's lots of things where the application you're doing, it wouldn't make sense to do like something where you drop down a dimension or go up a dimension or whatever like that. You just want to sort of maybe preserve the space as much as possible, even to the level of preserving distances. So what this thing in B is basically saying is like, Q operating on X for some vector X is, just the matrix transformation of that vector. So it's just moving it around in space. And it's saying that the magnitude of X post-transformation is the same as the magnitude of X originally, right? It didn't elongate the vector, it didn't shrink it or anything like that. It's just preserving the length of that vector. That's what that one says, right? This last one, okay, the way you want to think of dot product really is sort of how much of like X shows up on Y or how much of Y shows up on X. And it's really just a scalar of that measurement. It says, how much of this do you see here and how much of this do you see here. And so what it's saying is that if you do Q times applied to X, right, so you get this vector out here, and then you do this, get this vector out here, what it's saying is the Q that we add in here, basically is not giving you any more of X on Y, or not giving you any more of Y on X. It's literally equal to that original dot product, which is nice. All going back to just length preserving ideas. And these really do show up all over the place. I feel like a lot of the most kind of normal applications of matrices, which is not the kind that I actually used them for, but if you go be engineers and things like that, a lot of your matrices will be orthogonal. They're very common in like everyday kind of computations with math and stuff. So yeah, basically just think of Q as a transformation, but one that's going to like preserve distance. All right, so in order to prove this theorem, I'm going to take kind of this approach. So if you're proving equivalence things, you basically need to, I mean, the most direct way is like A implies B, B implies C, and then C implies A. But there's lots of other ways to do this. I'm going to go A implies C, and then C implies B, okay? And then I'm going to say B implies C. So basically those two things are equivalent. And then once B and C are basically shown to be equivalent, I can either do C implies A or B implies A. It doesn't really matter at that point. So I can kind of either go down A to B to C and then C to B to A, is what I'm saying, or I can go A, B, C, and then back to A. But somehow you need to get through all of those, right? So the first one I'm going to do is just assume Q is orthogonal and show this magnitude, show this dot product one happens, okay? And so what we're basically used for our orthogonal definition is just what we have, well, no, I thought it was on this page, but, so I mean, it's sort of on that first page, I guess, but this is what we're going to say. So if Q is orthogonal, then we know that QTQ equals IN for some n by n, okay? That's really like the definition of orthogonal. Like, its transpose is basically acting as the inverse is what it means, okay? So now I'm just going to kind of get in and just start. So if I do QX dotted with QY, I'm going to use that duality understanding of dot product that we saw earlier in the year, that there's this connection between transpose, which is why I'm bringing it in, and dot product. So I can also write this as Q X transpose, right, times QY. And I always like these things in math. Transpose is always, transpose and dot product is like a cool duality, but there are a lot of these other dualities in math that really help you like do cool proofs and tricks like this. So if you like this, you should be a math major. It's cool stuff. Then I'm just going to use like the socks and shoes property of transpose. So just simplifying, I would have this, right? And this is where I'm going to use this result, right? So just by the above line there, I can simplify this to X transpose Y, which we know is X dotted with Y. And that does it. So very much just kind of a symbolic computation proof, but you know, probably if I was writing out, I might add a few filler words in here and be like, you know, the dot product of this due to duality can be written as this. Then using socks and shoes, we simplify to this. And then since QTQ is I sub n, we simplify it to that. And then again, we use the duality of the transpose and dot product to get to this. So that's kind of how, if I was writing it up really, really nice, I would do it, but this is fine too. So that proves A implies C. All right, so now I'm going to show B and C are equivalent. All right, so I'm going to start off and prove the, Yeah, sorry, that is the way I want to do it. So B implies C. I'm going to use a weird identity here. So way back in section, I think it's 1.2, there's an identity that says, like, for all vectors x and y, we have this identity where or x dot y is equal to a fourth of the magnitude of x plus y quantity squared minus the magnitude of x minus y magnitude squared. I actually did give this as a homework problem. It's really not too bad to prove it. It's just sort of a symbolic, sort of rote, sort of straightforward proof, equivalence kind of thing. But I'm going to use that to use B to show B implies C. Okay. So a lot of these things too, like why I would ever think to use something like this is really you're just trying to think of how can I get what I want to show into the problem. And this is an important thing with the dot product. And, you know, it's tricky to pull this out of thin air, but sometimes you just try things and then it doesn't work, and then you try other things and eventually it works. But I'm going to use this to get me started. So I'm going to copy down what I just wrote there. All right, so just saying that where you know that for all vectors x and y, x dot y is equal to this identity, which again, you can go back and look at it in the book there. And then this is where I'm going to, so I'm assuming, we assume basically the magnitude of qx equals magnitude of x, right? And this is also the reason why we would use this, because it involves a magnitude, right? And so what we're going to do is we're basically going to have, instead of, that's for every x, right, in B. So x could just be x plus y, basically. And so what I'm going to do is I'm going to say, well, since this is true for all x, all vectors, right, then it's true for this vector in here and this vector, right? So I can just say something like, using B, right, then x dot y equals 1/4 magnitude q x plus y magnitude squared minus magnitude q x minus y magnitude squared, which we can simplify here a little bit. I could say qx plus qy minus magnitude qx minus qy. And now I'm actually going to just write the answer, and I'll explain why. So this thing up here works for all vectors x and y. Now, what I've done is, just by introducing b, what we assume, we get this q in here. And so these are now my vectors, sort of like my x and y up here, right? So qx is like x, qy is y, qx is again like x, qy is y. And so this is an equation, works this way. This is equal to this, just like this is equal to this. And so I'm just sort of using it in backwards direction there, but that would do it. So all you do is you sort of start off with that identity, and then you just assume that B holds, so you can introduce a Q in there, and then you just use the identity one more time. That does it. That does the forward direction. And then for the reverse direction, we're just going to assume that qx dotted with qy equals x dot y for all x and y, basically in Rn, right? And then all we're going to do is we're just going to let, it's true for all, right? X equals y, and basically note, right, that we get qx dotted with qx equaling x dot x. Then we can just say, therefore, the square roots of these things should be equal, right? It's just if the numbers of these scalars are equal, then their square roots are. And we know that the magnitude of let's just don't even need to bring Q into it. Magnitude of some vector z, right? Squared is z dot z, right? So if we, I'll say it like this. So the magnitude of z is equal to the square root of z dot z, right? So then we can just say, then by above, notice we have the magnitude of qx equaling the magnitude of x, right? Which does it. Just saying that, if these two are equal, just based on these two being equal, which again is because we assume it in C, then just using this identity sort of thing that we know from dot products and things, we can write this way, right? And then if these are equal, then these are equal, right? So that would do it. So now we've got A implies C, and B and C are equal. All right, so what we're going to show now is we're going to basically have that, we're going to go back to A, and we've already shown that B and C are equivalent, so really I can say B/C implies A here. That's really the way to say it, because they're really the same thing. So what I have now at my disposal is anything in B or C, and I can use those to show A. And once I do that, then I've shown all these are equivalent. So what we're basically going to do is we're going to show that, so I'm going to just denote oops, that's not the letter L. Let Q sub I and Q sub J denote the ith and jth columns of Q, respectively, right? And what I basically need to show is that if Q is orthogonal, whoops, that is not what I wanted. If Q is orthogonal, then any two columns, right, or rows even, but we'll just do columns, they basically form an orthonormal set. And so I basically can dot product any of these things, and I get 0 or 1, 0 if the i's and the j's are different, right? That's like the perpendicular dot product. And then 1 if the two I and j's are the same, right? So that's basically the plan. And so for this, there's kind of one thing you need to notice. Let's take I'm just going to make up 2, 5, 3, 1. And if you multiply by 1, 0, right, then what this does is it basically will pull out the first column, right? So if you just literally do it out, right, you do 2 times 1 plus 3 times 0, you get 2. And then if you do 5 times 1 plus 1 times 0, you get 5. And you can extend that to higher dimensions. You could also do 0, 1 and get the second column, okay? More generally speaking, if we kind of use that standard notation where E sub I is the ith standard basis vector, we could say something like this. Note Q times E sub I equals Q I, right? Where E sub I denotes the ith standard basis vector, right? And so now, if you notice that, then we can finish this off with just some straightforward kind of computation. So, so Q sub I dotted with Q sub J, right, equals This is just using what is here in orange, okay? We're going to be able to write, that's the same thing as Q times E sub I, dotted with Q applied to E sub J, right? And then this is where I actually use property C, okay? So property C says that this should be the same as E sub I dotted with E sub J. And we know that those are the standard basis vectors, and we know that those things equal 0 when I doesn't equal J, and are 1 when the two of those are equal. So if you look at what we just said there, right, basically this shows the columns of Q form an orthonormal set, so Q is orthogonal. Does it? So I think all of these proofs are pretty enlightening and pretty good. They show good proof techniques and whatnot. So, but I don't want you to get lost in what everything is saying. If you just look at them for face value, this thing says for orthogonal matrices, the magnitude of Q applied to a vector is the same as magnitude of the vector. Did not make it bigger or smaller. And likewise with dot products is a measurement really of how much of one thing shows up on another. And because Q doesn't make vectors bigger, it's not going to make that dot product bigger. It's going to be the same this way as it is this way. So, but to prove that takes some weird tricks and also weird identity and things like that. So a lot of this is just good proof technique demonstration. All right, so we can actually use this theorem to do some cool things kind of now. So this is just some more properties basically of orthogonal matrices, and I will show some of these in the next video too. But we'll just kind of run through the list really quick. It's saying if Q is orthogonal, then its inverse is orthogonal, which shouldn't be surprising because the inverse is a transpose, and the rows and the columns of an orthogonal matrix they form an orthonormal set. This shouldn't be too surprising because determinant measures, it's like a scale factor of the area change in the transformation, right? And it's basically, if it's plus or minus 1, it's saying there's no stretching sort of going on. There might be a directional change to things, right? Like you could flip a unit square over the origin or something and move it to a different spot. That could be like a negative determinant. But the unit square wouldn't change to like a 2-unit square or something like that. So that is kind of related to the length preserving, isometry of these orthogonal matrices. This also shouldn't be surprising. Orthogonal matrices should have an eigenvalue of 1 because eigenvalues represent that scale factor change with a vector specifically. And if you're not doing that, then it should be 1. That's like the value that represents things stay the same, right? And then this last one says if Q1 and Q2 are orthogonal, then their product is, which is very handy. And up here I basically just say this is more ways to say that Q keeps things the same. I want to actually just prove C right now because it's a cool application of what we just did in the last kind of equivalence theorem. It uses part of that. Specifically, we could just say based on the previous theorem, note magnitude of V is equal to magnitude of QV. Okay. And then if there's some sort of eigen stuff happening, we know QV equals lambda V for eigenvector V and eigenvalue lambda, right? And so what I can do is I can take my magnitude v, which equals my magnitude qv, and pop in now lambda v, right? And we have like a similarity between magnitudes and absolute values. So when you have a scalar, right, you're taking the magnitude of a scalar, it really, in math language, we call that absolute value. And so we can pull that out as a positive lambda. And so I'm just going to say, like, so note, all that happens, okay? And then the only way magnitude v can equal absolute value of lambda times magnitude of v is if lambda, absolute value of lambda equals 1. That's what I want to say. And so that does it, right? This just uses that property b right there, right? Because it's true for any vector in Rn. So we're just basically assuming it's an eigenvector, and then we would get this identity popping up, and then just property of absolute value and magnitude. So, yeah, this is very good, I think, to help you understand what an orthogonal matrix is doing. And really this does too. A lot of these things, you should see a connection between what they're saying and this idea of like length preserving.